And what are we going to say here now? 241. I think what did I put? I put these worksheets here last night. And rectangular and polar curves. So what I'm going to need to do is go to my settings. Turn my Bluetooth is on. Okay. See this rectangular polar curves? I got to talk about this. I'm going to bring in, where are we at? There we go. I'm going to bring this in the iPad. So I have to go to, I think I clicked on that and I have to share it via AirDrop. And yes, I have to bring it in, nullability, create a new note, import. Now we're good to go. Wow. So remember what I was talking to you guys about, that the reason you got to go to polar is because, in all honesty, there's a lot more beautiful, complicated curves that exist. Like, for example, and we're not here yet, but if I said to you guys, some of these curves exist in the polar world, but we don't have equations necessarily that work very well algebraically. They're not very simple. So we're going to have to learn another coordinate system just to talk about these other kinds of curves. So I'm going to start, ladies and gentlemen, with this kind of exercise saying to people, hey, what kind of curve am I? And so what I'm really doing is saying to you the following. Let's go back and read. It says this: we can look into the various polar coordinate curves where this is function notation here. R is f of theta in relation to the rectangular coordinate curve y is f of x that we're familiar with. So we're familiar with y is f of x. We spent our whole life up until this point in algebra, plotting, like, for example, lines, parabolas, log equations, exponential equations, circles, ellipses, hyperbolas, parabolas. I think we said that. Graphing polynomial functions, rational functions. If you're taking pre-calculus, there's a lot of curves. Those are rectangular. Polar makes things easier to some degree for some situations. Okay? So you have to be able to kind of think about that, I guess. So there's a relationship between the two formulations. We already started working with this. We have the conversion formulas. We know what that is. But what I want to go back to you guys with is something also interesting. If I go back over here, let's find it. That original worksheet here. Based on, there we go. We have more information here. Okay? X can be described as, or let me use the definition here first for, isn't cosine theta equal to x over r, by the way? So you know what that means? X can be described as r cosine theta if we look at this algebraically. Just from this triangle here. Similarly, we know sine theta is y over r, which means y can be described as r sine theta. So I want to talk about this as well. All this from this what? Right triangle. So x is our cosine theta, y is our sine theta. Okay, we're going to use that here. So I'm going to write that down as well. We say, oh, x is our cosine theta, and y is our sine theta. Okay, so we know what this is. So if I say to you, okay, we got circles. This is actually, I think it's probably good for you guys to know this. You know what C is? C is a constant. So if you ever have R equals a constant here, C is a constant, R is 4. You want to know what curve that is? Because they're saying, what curve am I? Let me share with you guys what happens when R is a constant. I can square both sides. What happens if I square both sides? I get R squared equals what? 16. Is that true? If I square both sides? Well, what is R squared anyway? Have you ever seen R squared before? Say yes, we know what that is. What is that? That's x squared plus y squared. How do you know? Because you're looking at that relationship right here. X squared plus y squared is R squared. And in fact, if you just simply said, Mr. Judge, can I just plug in 4 here for R, and I get my x squared plus y squared equals 4 squared, and I'll say, I guess you can. Yeah, that's fine too. But what you end up with here is x squared plus y squared equals what? What's 4 squared? That's 16. What curve is this? Do you guys know? This is a what? It's a circle. Centered where? The center is at the origin, and the radius is 4. So this is just an example, but if you ever see R being a what? Constant, you know the radius is 1, 2, 3, 4. So you can go all the way over here. Go on the other side. 1, 2, 3, 4. There we go. It's a circle. And there it is. So here's my point to you. This equation of the circle in rectangular coordinates can be a lot easier described in terms of what? R is 4 in polar coordinates. That's just a constant. Okay, you guys okay with that? And this is going to be 4, negative 4, 4, negative 4, those particular points, because you have a circle centered at the origin. And there you go. R is a constant. R is negative 3. You say R can be negative? Yes. What happens when R is negative? Well, R squared becomes negative 3 squared. Or R squared is 9, which means x squared plus y squared equals what? 9. What is this? This is a circle centered at the origin Radius now is positive 3. So you actually can have a positive 3 or a negative 3. There you go. There it is. Now you might say, what am I looking at here? You're looking at the equation r is a sine theta. This is a polar form equation. You say r is that f of theta here, okay? They give you that equation in polar form. But the question is going to be again, what is this? In this example, this is r equals 2 sine theta. So here's what I'm going to do now. I'm going to take this r equals 2 sine theta. Again, I'm going to say to you guys that this is going to be a circle. So I start with circles. This is an equation of a circle, but it's not going to be at the center. Now, what I'm going to do here is this. I'm going to multiply both sides by r. You say, what do you mean? That'll give me r squared again, but then I get 2r sine theta if I multiply both sides by r here. Okay, you already know what is r squared. You guys know what that is? That's x squared plus what? Y squared. And that equals 2r sine theta. R sine theta. What do you guys know about this, r sine theta? R sine theta is what letter? Y. This is why I had to point those details out to you guys. R sine theta is the y variable. So if I go back here and I say to you, because we want to know what curve is this is the variable of what? This is y. So you get what? X squared plus y squared equals 2y. So they're going to ask again, what curve is this? The y value. See that there? Now, any of you guys taking pre-calculus? No? Okay. Any of you guys taking intermediate algebra, maybe? Let's go back here. On my website, believe it or not, in intermediate algebra worksheets videos, I have a topic called, oh, what is this thing called? Complete the square. And I demonstrate to people how to complete the square here. In fact, so there's how to complete the square. And of course, you guys have a video here. And then even in conic sections, you do it here too. In some of these, of course, you have a video as well. So, you know, I do have some resources where you guys can actually do those things. That's what I'm saying. You got the video solutions here for every one of those. So you might say, what does that have to do with me? I'm in trig. Well, let's say you have to complete the square. So in order to do that, though, we have to subtract that 2y. Do you guys remember how you complete the square? See this value? It's B. What's step 1? Negative 2 over 2 is negative 1. Okay, complete the square. Then square that negative 1. You take that B over 2 value, you get positive 1. Okay, so you start with B divided by 2. Okay, you're going to end up using, I'm going to use this number here, 1. And over here, I'm running out of colors. This is an important detail. This is a complete the square process. So remember, we're completing the square with the y variable because that has the linear term, power 1, linear term. Leave some space. What do you guys use? Do you guys remember? You use the 1. So you add 1, you subtract 1. You always use this one first. Now, what I tell those intermediate algebra students, right in here, you're supposed to what? Well, you're supposed to factor, but don't really factor. You have x squared plus y in parentheses squared. That's minus 1 equals 0. Don't really factor. Do you guys know what you do? You use the value found in step number 1, which is minus 1. Well, we will. But here's what I'm saying to you. Completing the square gives you everything that you've seen here. But yes, you said, well, what do I do with this 1? Well, bring it to the other side, and you now have x squared plus what? Y minus 1 squared equals 1. So I'm going to ask that question again. Okay? What are you guys looking at? Do you guys know? You have the general equation of a circle. You say, what is that? It's x minus, I'll say h squared plus y minus k squared equals 1. Okay? So the center is at h and k, and the radius is going to be, r squared, and the radius is r. HK. So you might say, well, where is this? Well, this is at 0, 1. There's 0, 1. Radius was 1. So what you're really looking at is a circle right there. All right. And then similarly, you have a circle here. Well, this is another example of that. You got the cosine. Yeah, here you go. Similarly, this is the equation of a circle as well. So I'm going to have to express to you guys where this comes from, what this is, because look at this example. R is 4 cosine theta. And classically, how we verify this, these are circles. Multiply both sides by r again. Now you get 4r what? Cosine theta. Okay? You know what r squared is. R squared is going to be what? Yeah, x squared plus y squared equals 4r cosine theta. Okay, so we know where this portion comes from. But then I think I'm going to have to use, what color? I think I have to use orange. Why do I use orange here? What is r cosine theta? That's your x coordinate. So the equation is x squared plus y squared equals 4x. Okay? Because that's x. Remember, x is r cosine theta. So you subtract that 4x from both sides again. And ladies and gentlemen, you get x squared plus y squared minus 4x equals 0. I tell my intermediate algebra students, put your x's together, and then you get your y squared. Now, what do you do here, ladies and gentlemen? You're going to what? Complete the what? The square. You're going to complete the square. Okay. Now you say, what do I complete the square with? Let's get the colors here. You see this here? This is that first power. So you're going to complete the square with the x variable. And the process, again, b here is -4. So I'm going to take -4 divided by 2, which is -2. And then the second step is going to be to do what? Take -2 and square it, you get +4. So x squared minus 4x, leave some space here. And I forget what colors we were, I think that was red. So I always tell that class, what you do here is you add the 4, you take the 4 away. Okay? And the first 3 terms now, you're supposed to really what? Factor. But don't really factor. You use the value found in step 1. This is completing the square. So the value found in step 1, this is a -2. Then you say what? What do you have left? You have that, I got to get my eraser, which don't forget, you really have -4 plus y squared. And as before, you add your 4 to both sides here. So you're now going to get x minus 2 squared plus what? Y squared is 0. Sorry. Is 4. Now you say, what is this? This is a circle centered at 2, 0. Radius is 2. So now you're centered where? Centered at 2. Radius is, well, radius was 2. Because if it's equal to 4, you got to use that square root formula. Okay, you see this here? This is going to be the equation of your circle. Radius, this is r squared. Okay, r squared is 4, and your radius will be that +2. And, you know, sometimes what books will do, they write it this way. They'll say x will be, let me do this. R is maybe, I don't know, they write it as 2b cosine theta. So here b is going to be what? 2. And then they'll say, it'll be x minus b squared plus y squared equals r squared. So they kind of give you a, you know, if you notice here's 4, that means b is 2. There's no accident that this location is at, the center is at 2. Anyway. Doesn't really matter. If you just complete the square, you don't have to memorize any special forms. You just have to memorize, ladies and gentlemen, the following. So you say, what do I have to know? Well, R is B cosine theta. R is a what? Sine theta. R is a constant. What are all of these equations of? These are all what? Circles. Now you might say, why do I care about this? So again, when you go to other classes, they work with polar curves, and you'll start to see some of these here. And I will make sure I put some on your what? Study guide for test number 4. Here's another example, 6. And if you're really interested, notice how I did this. Here's another equation of a circle. And that's where you have an arbitrary center. Your center is going to be here at A and B. Radius is R. So this gives you your center, by the way. So you got circles 7 and 8. Anyway. You might say, how do I handle this one? Same way. Complete the square. Multiply both sides by R. You'll get 2AR cosine theta. And let me write it. I know we're out of time, but let me share with you guys this final thought. 2RA cosine theta plus 2RB sine theta. R squared is going to be 2RX plus 2RY. X squared plus Y squared equals what? 2RX plus 2RY. And then you say X squared plus, subtract the terms. X squared minus 2RX plus Y squared minus 2RY equals 0. And then now you complete the square with the X variable. You complete the square with the Y variable. And you can actually deduce the equation here that we're talking about. X minus A squared plus Y minus B squared is R squared. And anyway, I think I left out I think I screwed up. Yeah, I did. This is really going to be A, B, A, and B. So we can say now just complete the what? Square. And even our iPad is going away. Okay. All right, you guys, take care. Stay safe. I'll put your homework online in Canvas, and we'll see you guys tomorrow. You guys know what I mean? So it doesn't change. So it doesn't change. Just get used to it. Embrace it, ladies and gentlemen. I know I used to think to myself, boy, when I'm done, I'm never going to do work again. You know, and boy, was I wrong. Okay? Boy, was I wrong. Anyway, let's get some work done. Remember this form here, ladies and gentlemen, that I gave you here. This here, the way I look at some of these, I think it's important. We're looking at this yesterday, okay? This is really, again, a circle. So personally, if I were you and I said, okay, I'm really highly motivated to understand this topic, okay? That's actually the polar form of a circle in general. And you might say, what do you mean? This is polar. And I don't remember what color we were using for all this. This is a polar form of a circle. And then over here, ladies and gentlemen, this is the what? That's the rectangular form. The rectangular. This is the one, it's Cartesian coordinates, also known as rectangular. Rectangular coordinate system, because they should really call it the square coordinate system, personally. So it should be called the square coordinate system, and this should be called the circle coordinate system. So you got polar, and formally it's Cartesian. It's a French word for, I think it's a French word for square. I got to look that up. Cartesian coordinate system. It's a French word. Like Parisian, Cartesian. You guys know what I mean? So this is the one we studied in like intermediate algebra and in pre-calculus if you're taking that, but it's studied in intermediate algebra. I'm teaching it, in intermediate algebra. So you go, my God, this is another circle? Yeah, it's a circle centered at the origin, radius, not the origin, sorry, centered at AB, radius R. So if I were you, maybe I'd put it on flashcards if I said, but let's actually go through a detail here, okay? So I want to go through this particular example at least, and I'm going to prove to you guys that it's really a what? Circle. I'm going to prove to you what this is, okay? So we're given R is 3 cosine theta plus 2 sine theta. What you do is you multiply both sides by R. And what you end up getting would be R squared is really going to be 3R cosine theta plus 2R sine theta. So if you said you multiply the left by R and the right by R, that's what I'm saying. And then you get 2R sine theta as well, because you distribute that product with R, okay? You distribute. Just sharing with you guys that this is really a circle, okay? And so here's where you're at. Now, remember what we said yesterday. I forget the colors, whatever. If you see R squared, what does that mean? You replace that with x squared plus y squared, okay? This is the R squared portion, going back to the conversion formulas that we looked at. You guys agree with that? You guys remember that? And then you say, well, what is R cosine theta? I think I colored that orange. What is R sine theta? Well, you know what you get. This is going to be 3x plus 2y. So this is the x coordinate, by the way. And then this is the what? The y coordinate. So you're really looking at here, x squared plus y squared is 3x plus 2y. And, I know this is going to be a final exam question for Math 125 when I teach intermediate algebra. I give them this equation, and I say to them, hey, graph it. And then they freak out, and they go, oh, I don't know what that is. And it's like, no, it's a circle. In fact, I'm a lot nicer to them. I give them nice even numbers. But anyway, you'll see what I mean. So what you do is you subtract 3x and 2y from both sides. I'm going to do this little arrow thing called translate. So this will be x squared minus 3x plus y squared minus 2y equals 0, ladies and gentlemen. Okay? And that's how you start, because at this point, I'm going to say this. You have this to do and this to do. You say, what are you talking about? What do we say we do here? Do you guys remember? You complete the square. Okay? So if you guys remember this, I don't know. Are you guys taking Math 260? Anybody? Anybody taking Math 260 pre-calculus here? Nobody? Okay, good for you. You're not taking 260 at the same time? No one? Okay. Did you guys ever take pre-calculus in high school by any chance? Okay, did they talked about complete the square, right? Yeah, to some degree. But if you were taking 260, you'd really say, oh yeah, complete the square. But I know I do it in 125 intermediate algebra. So it's done there too, complete the square. So, all right. And so we got really in terms of the x coordinate and the y coordinate. So remember how this is done. This is for the x coordinate here. Okay? You're taking this b value. They have b values here. This is the b value. This is for the y coordinate, the b value. So I have two complete the squares to do. So it's negative 3 over 2. That's the first part. The second part is to square that. And that will gives you a 9/4. I typically do this and say, hey, that's red, and then this is purple. And I did have a video, I think I shared with you guys yesterday about that. So this is for the x coordinate. We're going to use that here. I'm going to do the y coordinate 2. That's negative 2 divided by 2. Well, we can do that arithmetic. That's negative 1. And then I square negative 1, and I get positive 1. This is the process known as completing the square. So we get x squared minus 6. Now for the x, we add 9/4. We subtract 9/4. So this is the process. It's kind of like saying, hey, this is 0. It's not even there. That's for the x squared minus 3x portion right here. Okay? And then you say, okay, what about the other one? Well, that's going to be what? Plus y squared minus 2y. You're going to add 1. You're going to subtract 1. Okay, so we're doing the y as well. So in red, it's here and here. And of course, that equals 0. Okay? So I think we're okay. Now, remember in complete the square, here and here we say factor. But you don't really factor. The nice thing about the complete the square process is you just use the value found in step 1. Okay, so notice this. This is the value found in step 1. Oops. Right in here. And this is the value found in step 1. Oops, we haven't put it. Don't forget minus 9/4 plus the value found in step 1 is minus 1. And don't forget there's a negative 1 there. Here's my point. It's a negative 1. Okay? You don't really factor. You're using the value found in step 1. With the rest of this, though, you say, what do I do with the negative 9/4 and the negative 1? Well, you're going to do arithmetic there. And if you want, move the terms to the other side, okay? In other words, add the 9/4 to both sides or move it. On the other side, it'll be positive. Add the 1 to both sides. On the other side, it'll be positive. I'm just going to do these arrows known as translating, okay? And then now I'll do my arithmetic here. So, all right, you say, what happens with the arithmetic? I'll take 4 over 4, and then this gives you 13/4. Is that right? X minus 3/2 squared plus y minus 1 squared is 13/4. And I'm just going to say, ladies and gentlemen, this is, by the way, the equation of a circle. The radius, though, if you say, what's my radius? Center is at positive 3/2. 1. This is, I'll put C for center. And then if you say r squared is 13/4, your radius is positive here. So even though we'll use the square root formula, the radius is the positive value. You guys will see this is really the square root of 13/2. So equation of a circle centered at 3/2, 1, radius square root of 13/2. Okay? So, okay, this kind of makes some sense. Because if we look at this portion here, right? You say, Mr. Judge, you have 2a and we have 3. And you said the center's at a. Yeah. If 2a equals 3, what does a equal? 3/2. And you say, oh, and over here you have 2b. Let's highlight it. 2b equals 2. Yes. If 2b equals 2, what is b? 1. So sure enough, a is 3/2, b is 1. If you're awake, ladies and gentlemen, if you're awake and you already know the form, 2a cosine theta plus 2b sine theta, guess what you can do? You don't have to complete the square. Oh my God, does that make some sense? Wow. Well, at least you get the center. How do we get the radius? You can get the radius, though. Can we get the radius? I don't know. Maybe you do have to complete it, but think, how would you get the radius here? Your radius of your circle. Guess you do have to do some completing of the square there. So anyway, I can figure out the center here. 2a, -4. The center, a is going to be what? -2. 2b. 2b is 3. Oh, b will be what? 3/2. So my center will be -2. 3/2 in this one. But the radius of the circle, we got to think, how do we get that radius? R squared is x squared plus y squared. Maybe we do have to do some completing of the square to get that radius. Anyway, so I just wanted to go through some circles here with you guys, okay? That's the equation of a circle. That's not at the origin. The origin is when r is a constant, like we seen yesterday. Okay? Now, the last thing I want to talk about, at least initially here for you guys, is how do you get lines? This is a line, if you guys notice here, theta is a constant. This is the form in which you get a line through the origin. Okay? So this is the general form right in here, a line through the origin. Theta is a constant. Like for a circle, r is a constant. We've seen that circle centered at the origin, radius r. This is the simplest form you can get. Theta is pi/4. So here's kind of the idea behind it, okay? Like in a calculus course, I'll say to people, this is where pi/4 is. You guys remember? So theta is pi/4. That's where pi/4 is going to be. There's no R value. So R is arbitrary. So all of those radius values are here, points on the line. There's infinitely many radius values that are positive, infinitely many that are negative. Those are all points in the line. Theta is what? Just pi over 4. That's kind of how we think about it. But if you said, how do I apply this in algebra? What's the equation, right? Well, remember, what is tangent theta going to be? Ain't that y over x? So y would be tangent theta of x. So now you can say, can I plug in my theta? Yeah. What's tangent pi over 4? Isn't that 1? So the line represented by the equation y over x in Cartesian coordinate system is the standard curve there through the origin, right? And you guys see the xy plane there. So this is kind of how we can find the curve. And you say, what curve am I? Well, this is a line through the origin. And this is an important detail when you take like a calculus course. You study circles and lines and, you know, in polar form because they're easier to work with. And that's kind of why you guys have to study this as well, you know, because they're preparing you one day for that kind of course. And you say, well, what about this? What if theta is negative pi over 6? Well, you do the same thing. Tangent theta, in this case, negative pi over 6 will equal what? Y over x. You see, we know this is a line through the what? Through the origin here, okay? So if you solve for y, you say, do I need to know what tangent of negative pi over 6 actually is? Yes, and you multiply it with x. Take out that negative sign. Tangent pi over 6x. What is tangent pi over 6, by the way? Anyone know? That's like saying tangent 30 degrees. So, personally, when I say to you guys, go back to this what? Special triangle. And that doesn't look right, but okay, who cares? In that 60, 30, 90, here's a 30 degree. This now becomes 1, square root of 3. What's tangent 30? So this is 1 over the square root of 3, or square root of 3 over 3, if we rationalize. So the curve is actually what you guys see here. Okay, this is the rectangular coordinate system. This is the one you guys know and love from algebra. 60 tangent 30 though, right? Because the angle is negative pi over 6. That's negative 30 degrees. So it's actually right here. This is the line here. Oops. Okay? Because this angle here, that's where negative 30 degrees would be, if you guys remember. Okay? But this is the rectangular coordinate version of that. So this is an important thing to be able to draw lines and circles here, by the way. And just to say, generally, you go, wow, Mr. Judge, you got this thing here. It's like a general equation. Oops, go back here. That is a general, this is the equation of the line, by the way. This is a standard form in algebra, right? This is the standard form of a line, and then this here is going to be what? You go, wow, I got R is C over A cosine theta plus B sine theta. Let me share with you guys where this comes from, okay? Just to kind of share with you guys how to convert that. Okay, so remember, we have this rectangular version. This is the standard form. Do you guys remember that? And then we know X is R what? Cosine theta. And we know R is, Y is R sine theta. We know that from yesterday. Here's the X. Here's the Y. Okay? So this becomes, if I replace X, I get AR what? Cosine theta plus BR sine theta. And of course, that equals a constant C here now, okay? So be sure now, focus on this R to factor R out. So that means R times A cosine theta plus B sine theta equals that C. You can now solve for R, and now you get C over here, this A what? Cosine theta plus B sine theta. So I'm just kind of remarking to you guys simply this statement here that, and this is more than apply, these are equivalent, okay? It's an equivalent relationship. It's a biconditional. So I kind of did, logically, I did this backwards for you guys. Sorry about that. Even though I use the word implies, it's a very technical thing. It goes the other way as well. It goes both ways. So it's equivalent. So this is kind of where that really comes from. You know. So again, if you said to me, hey, how do I kind of use this, right? In this, well, this is C, by the way. This is A, and this is B. Okay? So you say, oh, A is 2, so that means I have what? 2x. B is 3, so it's 3y equals C being 1. That's your standard equation here, okay? Standard form. And of course, you guys know you can graph that. You say, how do I graph that? Solve for y. So it's kind of, in my mind, if you said, what's a good way to know this stuff? Write those different equations down. And you could use the values of A, B, and C here with that. I got to go back and figure out that R. How do we get the radius without completing the square? I got to wake up for the circle. But anyway, that's your standard equation. Okay, just want to let you guys know. So we're going through an exercise here that's a great exercise. And you go, this is a parabola? Yeah. And again, I think I want to say that this is an equivalence relationship, a biconditional. This is a parabola. This is y equals x squared. And you say, how do I know that this is the polar form? Well, replace y with what? R, what is that? Is that R sine theta? Replace x with what? R cosine theta. Okay? Just to kind of let you guys know, this is y. That was y, remember? Replace y and x. So R sine theta is R squared what? Cosine squared theta. And really what you do to share with you guys that this is a parabola, subtract that R sine theta here. And that equals 0. You can factor the R out and you get R cosine squared theta minus sine theta, and that equals 0. And then you use the 0 product rule here. Sorry. This means R is 0. And this is R cosine squared theta minus sine theta equals 0. You can solve for R. R cosine squared theta is sine theta, or R will now be sine theta over cosine squared theta. So you say, wow, Mr. Judge, I can really represent a parabola? Yes. In polar? Yes. Do you guys know, what is R equals 0, by the way? You guys know what that is? Yeah, it's the origin. Theta, this is for any theta, by the way. So you're saying, hey, is that point there? Yeah, it's there. That's the origin. And then you have your parabola, centered at the origin, because that's y is x squared. So you can actually use this form for your parabola, So it's kind of an interesting kind of thing here, ladies and gentlemen. But, to remark, if I go back, because remember, I'm redoing the Trig web page on my website. So even if you go to worksheets and videos, you go, hey, that looks very different. I'm going to try to separate a lot of what I did here. The files are still here. But polar graphs, I think right here, polar equation conversion here. What did I do? For some reason, maybe I have to hit play. Yeah. You essentially get the same line. Does that kind of look familiar? Does that look familiar to you guys? I'm going to put that in the chat. I'm converting y as x. So I already have a video for a lot of these conversions here. Okay, you guys see that there? R equals 4 cosine theta. Oh, we're going to complete the square. I'm saying, what is this? Is that the volume's down? Y squared. Remember that from yesterday? Pythagorean theorem? You guys want to close that door? Yes. So that's another thing you want to recognize. You want to recognize all of those relationships. So you hear a little volume there on that one too. So I do have more if you guys want to see more. Okay. And you got, what does R equals 1 over 1 plus sine theta become? So there is more you guys can look at if you guys want to see that. So I recommend that. So I already did some of these things here. Okay. So there's some. All right. Now you say, well, what should we do next? Well, here's what I want to kind of do next with you guys, okay? Let's go back at our list here. Let's see what we can do. Well, first on the list is the cardioids. And so as you guys look at the cardioids, remember this. I'm going to get this in my end here. Okay. I thought I was. I'd have to do this here. I'm going to take that file and I have to share it. There we go. I got to share it via AirDrop. And, oh yeah, I want to AirDrop here. Except in Notability, create a new note called cardioids. And now, ladies and gentlemen, we're here. The magic of, boy, crazy. Okay, so if you said, where is that online? I got to put that online. What kind of curve is this? Do you guys know? When you see the word cardioid, what do you guys know? That means what? Heart. Don't ever have a cardioid arrest. Cardioid is like cardiac, also means heart. I got to look at the origin of those words. Cardioid and cardiac. Is that Latin? The dead language? I don't know. Cardioid and cardiac? You guys ever think about that? Like, where do these words come from? I do. Yeah, so am I, and English is my first language. You guys know what I mean? I'm a typical American. We barely know English. If you guys ever hear that joke, it's there's some truth to it. You know, it's kind of funny. Is like Europeans speak like 3 or 4 languages. You guys know what I mean? You go, wow, how can they do that? Well, probably because they all live close together, are close enough together, and they speak different languages. Isn't that amazing? Like, how could people so close together? I guess it's possible because even in countries like, even if you do like in countries that speak one language, there's different dialects of that same language. Did you guys know that? Isn't that weird? It's kind of weird. Different dialects of the same language. Well, I heard there's different dialects in China. I don't even understand. Right. Yeah. Isn't that amazing? And it's not even that far. You don't have to go that far. And there's a different dialect and you don't understand. So I guess that's a common thing everywhere throughout the world. It's common. Like even if you go to Mexico, do you guys know there's different dialects of Spanish? I heard that. I go, really? How could that be? Well, there just is. You got different dialects. You know, that's amazing to me. So I guess even in Europe, what they bother doing is they speak different dialects of European. You know, German, French, you know, English. You know, even in Russia and Ukraine, different dialects. You say, do I speak Russian? It's different dialects. I was watching this. I'll share with you guys something kind of interesting to me. I was watching, this is fascinating. The other night, I was watching, speaking of different dialects, people who live in the coldest, is it the coldest city, I guess? The coldest city in the world where people live is in Siberia. You know, and I was watching how these kids live. This is amazing. I was watching this kid growing up. They're showing this kid growing up in the coldest, where it's like negative 58 degrees. That's Fahrenheit. Something crazy like that, right? In the Siberian winter. Negative 58 degrees. This kid, he's probably about 8 or 9. They're sending him to school in negative 58 degrees. And you're like, wow. And of course, the parents are all concerned because you should be concerned. But there's a way you can live, and people do. And I was like, whoa, my God, watching this thing was amazing to me. And I guess the reason I'm thinking about it right now is because it's in Siberia, and Russian is something that these kids, they speak a native dialect that's in Siberia. They're not Russians. You go, are they Russians there? Well, it's a part of Russian. They're Siberian. They're different people. But they learn a dialect there locally, whatever that is. And then they got to learn Russian too. Interesting to me. So yeah, language. So when I think of the word cardioid and this word, I think of these words. To me, I like thinking of the origin. Where did that come from, that word cardioid? Because even how you spell it is, I always misspell it. But it's cardioid. That's not I-O-I. You know, that's not a part of English or even Spanish or European maybe. Maybe it is. Maybe it's Latin. Cardioid. Anyway, think heart. So whoever said mathematicians are not romantic people, right? So for Valentine's Day, you could use a cardioid. If you want to get a tattoo, get the cardioid. But this is the equation in polar form of cardioids. It's R is A. This is kind of how we see it, though. This is the formal way. This is one cardioid. Think of a heart. But this A we distribute. So you can see the way I see it is A cosine theta, or is A sine theta in my mind. And yes, you can see a subtraction. It's either plus or minus. That's why they do a plus or minus. All of these are cardioids, hearts. So, I'm giving you guys the notes on this because, again, I always think it's probably good to memorize some of this stuff, put it on flashcards, because it'll make it easier for you. And then when you go to a calculus setting, I'll leave this information up on my website. You can go, I remember that crazy trig instructor, because you're working with calculus of polar form one day, right? Maybe it's in calculus 2, and then calculus 3, the extension is in calculus 3. So this is why it's so important to go over this for you guys, because you see it in your future, okay? So you might say, okay, how do I know this is a cardioid? Very simple. This number and this number have to be the same. And then you see a sine theta or a cosine theta. That's it. But how they open, it's either open up, open down, open right, open left. There's 4 types because there's 2 for sine, 2 for cosine, that plus or minus. So in all honesty, you go back over here, and how I say to people how you do this, it's very simple. There's 4 types of cardioids because of that plus or minus. Two for sine. See that plus or minus? 2 for sine, 2 for cosine. So in this example here, let me do something to you guys to share with you why we got to have polar form. I haven't done that, but you see this first example. R is 2 minus 2 sine theta. I'm going to try to do it over here for you guys. See if I can do that, right? This is a cardioid, 2 minus 2 sine theta. This is in polar form. We're going to write this in rectangular form. So why you care about this, I'm going to demonstrate to you guys, okay? So they gave it to you in what? Polar. There's the polar equation. I'm going to write it in rectangular. You guys with me on this? I'm going to dare to do that. And you're going to understand why we're doing what we're doing. So you're going to multiply r to both sides again, right? So you say, do I multiply r to both sides like you did for the circles? Yes. That's the key. The key is multiplying r to both sides. Yes, you have to distribute. So you now get 2r minus what? 2r sine theta. Right? When you multiply r to both sides and then you distribute this. Okay, what do you do with this r squared? This is x squared plus what? Y squared. Okay, right in here. I know I'm changing the color on you guys, but the process is the same. Wasn't that the conversion formula? R squared is x squared plus y squared? And then I think I used green over here. What is this? This is 2r minus what? 2y. Okay, you guys okay with that? I'm going to share with you powerful translation. What does translate mean? Move that y term to the other side, and now you get x squared plus y squared. That's now plus 2y. I'm adding 2y to both sides. Okay, you guys okay with that? And the other side, it'll be positive. So this is a very quick and easy way to solve equations. Love translation. All right, we're almost there. You know what I'm going to do here? Do you guys remember from intermediate algebra or even pre-calculus? You're going to square both sides. So on the left side, you say, do I still have x squared plus y squared plus 2y, everything squared here? Yes. And what do you have on the other side? That's 4r squared. Right? 2r squared squared in parentheses. Distribute the square. 2 squared is 4. R squared is r squared. What do you do with what? R squared, ladies and gentlemen. That, again, is what? X squared plus y squared. So what I'm saying here to you guys is this. X squared plus y squared plus 2y, everything squared, is 4 x squared plus y squared. Okay? This is the very, very famous rectangular form of the cardioid that they want you to describe, represented by this r is 2 minus 2 sine theta. So I'm going to put it over here and say to you, I know you're looking at some other thing right now, but this is the Cartesian coordinate rectangular representation. So if you imagine, if you shared it with people, the ellipse, the circles, the hyperbolas, all those conic sections in rectangular form, imagine if we said, okay, ladies and gentlemen, I'm glad you made it today. Pretending you're in Siberia, coming in from the snow, 58 degrees, because you walked to school. And I put that up on the board and say, we're going to graph these. X squared plus y squared plus 2y squared is 4x squared plus y squared. People would flip because they flip when I show them a parabola. Why, you know, when you start to graph parabolas, people flip in general form. So, you know, if you said, wow, is that? Let's find Desmos. Where are you, Desmos? If we had to learn how to graph this in rectangular coordinates, let's put that in Desmos. Let's even see if Desmos knows. Desmos knows everything. So we put x squared plus y squared plus 2y, come out of that and square it, equals 4 parentheses x squared plus y squared. Sure enough, ladies and gentlemen, what do you guys see? Yes, exactly. Okay. You see a cardioid. Oh my God. But then you say, is this the same as r equals 2 minus 2 sine theta? Look at that, ladies and gentlemen. Toggle on and off, on and off. This is the polar version. Polar version, ladies and gentlemen. Okay? So which equation looks easier for you to look at? The polar version is a lot easier. And when you have to take a calculus course and you work with calculus in polar form, the reason you have it is because there's a lot of curves that exist that you haven't seen before in your life in which you could perform calculus with. But if you had to do it in the rectangular coordinate version that you guys have written in red, it would make the calculus a lot more difficult. But because you have the polar form, the calculus is a lot easier. And that's one of the reasons why you study polar and why you said, Mr. Judge, you spent your Thanksgiving doing all this stuff. Yes, because I know where you're headed and what you're doing. It's a very useful tool. And it'll be there forever. I'm going to put it up on the internet forever. So, you can share it with your friends and family, put it on social media. Let them know, hey, if you guys ever care about polar or STEM studies, you can do this stuff. And it's doable. You guys can do this. Okay? But if you said, how in the world do I graph this? All right. You take a trig class. You say, what do you mean? Well, you see this here, even though this is in what? Polar, right? I want you to go back and trig and say, go back to your trig class. First, second test, I don't even know. Remember this? Y is 2 what? Sine theta. Okay, you guys remember that? Go back to that curve. Y is 2 minus 2 sine theta. You say, well, what is that? Well, that's actually, if I just rearrange the terms. This curve is what you guys see right here. This is the key to graphing cardioids. In fact, this is the key to graphing most of the polar curves. I shouldn't say most, the ones that we study in trig. Because generally speaking, you can put a lot of different things for polar. You probably could get a PhD in polar form. But you guys remember how to graph this? That's the key. This is your key. Graph this, where this is your theta axis, and this is the y-axis. Or remember, we call that the x-axis here. Okay? So it's essentially your sine curve, but the amplitude is 2, but you got that negative sign. So it's what? It's reflected about the theta axis or the x-axis. And then you say, what about this plus 2 portion? Well, it's shifted up 2. And so you might say, well, what does that look like? It looks like what you see here in black. So the key, ladies and gentlemen, is to go back and graph this equation. Okay, that's the key. Now, remember, this is only, by the way, one cycle. Do you guys remember that information? You say, what's one cycle? Well, that's from 0 to 2 pi. So if you said, is that why I see down here, and I don't know what color to use? This is all 0 to 2 pi? Yes. Remember these important points here. This point, this point, this point, this point. That's where pi is. This is pi over 2. This here, 3 pi over 2. And then this over here is going to be what? 2 pi. Okay? Now, I'm going to do some colors here, okay? So this is one full cycle here. I'm going to do some colors. You say, what do you mean, colors? This is important here. 0 to what? Pi over 2. Pi over 2 to pi. We'll do pink. Pi to 3 pi over 2. And then brown here. 3 pi over 2 to 2 pi. Does that look, what? Does that look interesting to anybody? What is this? Do you guys know? This is your angle theta. But in orange, these are angles that are in quadrant what? That's quadrant 1 angles, Okay, you guys okay with that? Pi over 2 to pi or quadrant what? Pi to 3 pi over 2 is quadrant what? 3. 3 pi over 2 to 2 pi is quadrant what? 4. These are your quadrants. So what you're going to have to learn how to do is read this curve here. So all these important points that I have here in dots, important locations, I guess, we're gonna have to read. So this is about reading this curve. Okay? So this is the key. This is where you start. This is how we start to graph a cardioid. All right, now let me share with you guys what this means. Can I ask you what this address is here first? I guess I'm going to say, what's that address? Do you guys know? That address, if we think of it in polar, right? Polar is r theta. This is my y-axis. Think of it as r and theta, though. Okay? Think of the polar representation. So, because I'm thinking polar, do you guys know what that address is? Yeah, we need the radius. The radius is 2, and the angle is 0 degrees for this point here. Would you guys agree with that? What's this location down here? Your radius is what? 0, but the angle is pi over what? 2. So far, so good? Those are points that we have to consider in polar form. So, what this means is this. You're going from angle 0 to angle pi over 2, 90 degrees. You go from a radius of 2 to a radius of 0. So 2, 0, 0 pi over 2. Here's what I mean by that. Okay? So you start at 2, 0. Where is 2, 0 at? In polar, this is 2, 0. You guys okay with that? That's where you start. And then I have to rotate that pole, how? 90 degrees. So I'm taking this pole and I rotate it 90 degrees. And what happened to the radius? When I rotated 90 degrees, my radius went to 0. So far, so good? What does that look like? I went here. So my radius through rotation went from 2 to 0. This is the quadrant 1 I'm referring to. Quadrant 1 portion. So you start at 2, 0, and you went to the pole because the pole is 0 pi over 2. What happened to that radius during the rotation? It went from 2 to 0. Is that right? You say, how do I know? Because of this curve, it's telling me. I'm thinking of this as y is really the r axis. So all of these here is my polar coordinate points. That's why you have to learn how to graph in polar. And so you say, wow, Mr. Judge, that's amazing because that's exactly what we have here. This is that quadrant 1 piece. This is how you graph in polar. Now you say, well, what happened when you went further? Well, there's more to the story. You say, what do you mean? Look at the green portion, right? What's this point? We're going to go from this point, 0 pi over 2, to now my radius again is 2, and the angle is what here? This is pi. This is the angle. So I'm looking at the green quadrant 2 portion. So I'm going to radius 2, angle pi from the pole. 2 to pi. Now, you might say, I don't like you using that purple. Okay. Quadrant 1, quadrant 2. You guys okay with that? So I'm going from an angle of 90 degrees to 180, and my radius goes from 0 to 2. So you say, what does that look like? Well, this is already at 90. If I rotate to 180, my radius somehow goes back to what? 2. That's the location. Isn't that the location of what? 2 pi, because we learned how to graph. And then how does that curve look? It looks like this. The radius went from how? Zero to what? 180. 0 to 2. So you have to go back and read that curve here. And sure enough, this is the green portion. You say, is that how I get to green? Isn't that where 2 is? And you say, isn't that where this is the green portion? Yes. Easy breezy, lemon squeezy. Okay. Now, what's next? What's the next point we find? We got to read this. What's that location? That location, the radius is what? 4, and the angle is what? 3 pi over 2. That's the pink. So I'm going to go from 2 pi to 4, 3 pi over 2. What's 3 pi over 2? 90 degrees. Okay? So we rotate. Again, we're at 180. And we're going to rotate to, that 270. Isn't that 3 pi over 2? What happened to the radius? It's now what? 4. So you say, how do I find 4? Well, let me do this so you guys can see. Well, I think it looks like what? 1, 2, 3, what? Right here. This is 4, comma, 3 pi over 2. So when you rotated the angle, when we rotated to 3 pi over 2, the radius went from 2 to what? To 4. Sorry. You never guessed my parents are artists, but they are. This is that pink portion. Easy breezy, lemon squeezy. You're going back to that curve, but you're thinking of that as R, the R axis, and the theta axis. You're reading polar coordinates here. And that's why if you go back here, you go, oh, is that why I have this here on the more beautiful version? Yes, that's quadrant 3, ladies and gentlemen. Okay? Easy breezy, lemon squeezy. To finish off the cardioid, we're going to have to do what now? What's this address here? We're going to finish this. What's that location if we read it R theta? Well, R is what? 2, and theta is what? 2 pi now. This is the last portion of the cardioid. So you're going to go from a 4 radius to a what? 2 radius. When you rotate from 270 to what? 360. To 360, we go from the 4 radius over here back to what? 2. And that completes the what? The heart, the cardioid. The more beautiful version of it. There it is, ladies and gentlemen. There it is. So, we learned here today how to graph some what? A couple of things. We learned how to convert to the rectangular coordinate representation. We learned how to graph a cardioid. That's the process. Now, if we go back to my website, you say, Mr. Judge, I am so excited by what we learned today. Hopefully. Worksheets and videos. I do have at the very end there graphing polar curves. So I have spent some time. You say, how much time did I spend graphing polar curves? Well, we got some how to do that, how to do some more. Now, we're going to continue tomorrow. I think did I get that? No. What is this? Polar coordinates, polar equation conversion. I think this is just a graph if you guys want to help yourself with, maybe you said, I want to put this on a nicer what? I want to use what you have there. Okay, there you guys go. I have this kind of graph paper for you. But I thought I had that here somewhere. Go back. What does this say? No, that's parametric. Maybe that's the same one. I got to look for it. But I do know I do have some of that. But anyway, we started our graphing of cardioids. We're going to continue graphing cardioids when? Tomorrow. Then we're going to graph the others, lemniscates. We got how to graph lemniscates. Same process. Same process. How to graph the other polar curves, same process. So we're going to learn some classic polar curves. And now that should kind of make some sense. But remember, what is probably the hardest part for people? Right here. Remember, graph one cycle. Y equals minus 2 sine theta plus 2. And then say it's not y, say it's what? R theta. And you want to determine all of those points. Those are the points I even asked you guys when I graphed. What's the minimum value? What's the intercepts? What's the maximum value? Do you guys remember when you sketched these graphs? That's one of the reasons why you learned how to graph here. And that's one of the reasons why I asked you for all those particular locations. So it's all coming together. It's like baking a lasagna. We're pulling it out of the oven. We made the sauce. We cooked the noodles. We put the cheese on it. And now we put it in the oven and it's coming together here, ladies and gentlemen. So we're going to do more cardioids tomorrow. So ladies and gentlemen, I hope you guys enjoyed the demonstration. Take a look at your study guide because you'll see, hey, he put a cardioid there. Well, yes, I did. All right, now I'll let you guys go a few minutes early. So, ladies and gentlemen, take care, stay safe, have a wonderful day. remember? I'm looking at this stuff here now, and this is cardioids. Whoever said mathematicians were not romantic? Cardioids, okay? Send some roses and cardioids for Thanksgiving. We're even going to talk about roses, but I'm going to try to work another example of cardioids today. So we're going to graph some polar curves today. What do you guys think? First off, if you look at your study guide, they're going to ask you for the rectangular coordinate system equation for this. So if you said, you know, Mr. Judge, that's a what? That's of the form of a cardioid. Remember that the forms I gave you guys? It's on this worksheet, right? Where these numbers are the same. This is A, this is B. And you can have sum or difference and a sine theta, a cosine theta. That's a cardioid. That's the tip-off where A is B, where these values, we call that A and B. They're the same. So you go, oh, and then you're going to see a sine theta and a cosine theta. And yes, it's sum or difference. So, okay, it's a cardioid, but there's really 4 types. A heart that's upright, a heart that's upside down, one pointing to the left, one pointing to the right. There's only 4 types. You don't have to memorize that part, but I didn't even give you notes on that. So I'm just going to say the first thing you want to do, or the first thing I'm going to ask is, what is the rectangular coordinate version of this? I'm going to see if I have some space here. I might have to go to some scratch. So you guys know, what's the first thing you do? What did we do yesterday? I said multiply the left and the right by r. Yes, you're going to distribute on the right side, okay? And so what that gives you, if I go up here and try to use some of that space, we'll get r squared is 4r plus 4r cosine theta. Is that right? You guys okay with that? And then I said, here's what you guys always want to know. R squared is something, and I think this is orange. What is r squared? Do you guys remember? X squared plus y squared. Replace that r squared with x squared plus y squared. We did. Replace r cosine theta with what? What is that by definition? That's x. You guys remember that? And then you might say, I have x squared plus y squared is 4r plus 4x. Okay, so we're trying to convert everything to x and y. Now remember, you're going to subtract 4x from both sides. You're almost there. And now you have x squared plus y squared minus that 4x equals 4r. Okay? Almost there, ladies and gentlemen. We almost got rid of the r. We have x and y. Do you guys remember the step we did yesterday for the cardioid yesterday? Square both sides. So yes, square the left, square the right. Okay. Now you say, what does that mean? Well, don't actually square the left side by using FOIL. Just leave it symbolically squared. And now we get 16r squared, ladies and gentlemen, on the right side. What does that mean again? Replace r squared again with what? Yep. So I'm going to copy that. And then, ladies and gentlemen, here's the Cartesian coordinate version. X squared plus y squared minus 4x squared equals 16 parentheses x squared plus y squared. That, ladies and gentlemen, is the Cartesian coordinate version of what you guys are looking at here, this cardioid, or this polar curve. Remember, I think polar we did in purple or something like that, or pink. But notice again, this is the polar curve, and this is the equivalent rectangular curve. Okay? So could you imagine you showed up one day and said, we're going to graph these rectangular versions in terms of x and y? You're going to get people fainting because you're going to say, I can barely handle the parabolas, Mr. Judge, or the circles or the ellipses. Now you want me to graph this kind of relationship? Well, yes, but there's no technique that we have in rectangular coordinates. We have a technique, though, in polar coordinates. This is a lot easier. And that's why we're here. In all honesty, we're here to study that. Let me get out our Desmos. You guys like Desmos? I like Desmos. My gosh. You know, because if we go to even Desmos, if I said to you, boy, do you guys know what we have there? What do we have? We have parentheses, x squared plus y squared minus 4x. Come out of that and square it. And that's 16 now, okay? 16, now it's starting to say, hey, I got a clue of what you're doing. X squared plus y squared. And then sure enough, you say, hey, that is a heart, but this heart is what? Oh, sorry, this heart's beating. Sorry. This heart is it's opening to the left. It's like it kind of, so it's rotated to the left, really. And that's what's going to happen. You keep rotating this 90 degrees by the 4 different versions of cardioids. And that's what's going on here, ladies and gentlemen, just so you guys know. So anyway, it's easier to use the polar graph, and that's what we're going to study. Now, you say, what do you really do? Well, remember what you guys do with this. If I can get my eraser here. What you do is you go to the Cartesian version again. You say, this is y. Now, when we graph this is 4 cosine theta plus 4, right? So what you see here is that graph. This is the y-axis, and this is theta. Notice, yes, this is an upshift of 4. Is that right? So they took a cosine curve. Yes, the amplitude is 4. We know about that. We're going to have a final on it. Had it in test 2. And yes, they shifted the whole thing up 4. And this is only one cycle. So you only draw one cycle. You say, what do you mean? Well, theta is between what? 0 and 2 pi, okay? And there you guys go. But don't really think of this as y and theta. Think of these points, again, as what? As a polar coordinate. So these are all the points. So I'm going to change that y to r, but it's like graphing this in the rectangular coordinate system so that you can remove the points. In other words, remember this. That point is special. That address is what's the radius here? Do you guys see it? The radius is 8, but the angle is 0. You have to, this is now r theta here, okay? R versus theta. So that point was special. And then you say, what other points were special? Well, this point, and that's where pi was, or pi is. So here my radius is 0, but the angle is pi, okay? So we're looking at that as r theta again. And then this point was special. You say, why? Because the radius is back at 8, but the angle out here is 2 pi, okay? So this is where 2 pi would be here. So remember, when you graph this, we need these important locations. However, we also need not just 0, not just pi and 2 pi. We need pi over 2 and 3 pi over 2. Is that right? We need the 90-degree angle, and we need the 270 degree. So pi over 2, that's 1/2 of pi. Believe it or not, it's like right over here. And then over here will be your 3 pi over 2. Okay? So now the radius here is 4 when the angle is pi over 2, and the radius is also 4 when the angle is 3 pi over 2. So we have all these nice locations here, okay? This is what we need. So yesterday I used colors. I said, oh, the curve from here isn't going to be in orange. This portion we did from pi over 2 to pi, we said was in green. And then, what other color did I use? I don't even remember. Maybe here to here. And then finally, last portion here. All right, ladies and gentlemen, I'm colorizing this thing. So I don't even know if colorizing is a word. But the point I'm making is we need these locations. Here, 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 and here. There you go. There it is, ladies and gentlemen. And this is a cardioid. Now, remember, these are angles. 0 degrees to 90 degrees, you went from an 8 radius to a 4 radius. You go from, so for quadrant 1, because remember, this is all quadrant what? This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So from 0 to 90, you went from 8 to 4. That's the idea. So go back over here. You say, okay, in quadrant 1, we went from 8 to 4. So I hope I have 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. There's the location. 8, 0. And then we go to 1, 2, 3, 4. We go to 4 pi over 2. So bear with me. This is my art skills. And that is that first portion here. Okay, in orange. You guys okay with that? That's up here. You went from 8 to 4. And then from 90 degrees, you say from 90 degrees now to what? Pi, which is 180. Your radius goes from 4 to what? To 0. 4 to 0. So you say, okay, so how do I go now? I'm going to go now to 4, 0 is here. Remember, it's at the pole. So this is going to come somehow back to the pole here. And as you guys can see now, yes, our cardioid looks like it's on its side. Our heart is on its side. Is that kind of like a broken heart? No, maybe a broken heart's an upside down heart. It's on its side, almost broken. So let's read this now. What happened from pi to 3 pi over 2? So in quadrant 3, we go from 180 degrees to 270. Our radius goes from 0 to what? 0 to 4. So I somehow now have to go back to this point. 1, 2, 3, 4. And sure enough, I forget what color. What color was that? Brown. And then we ended with pink. So ladies and gentlemen, this quadrant here, quadrant 3, because this is our quadrants, remember? 1, 2, 3, and 4. So as you guys can see, this cardioid, it's taking its shape. Is that right? This is the location. 4, 3 pi over 2, right in here. And then we're coming back. We're going from 4 now to what? To 8. When you go from 270 to 360. 4 to 8. 270 to 360. So somehow we went back to what? Over here at 360. Radius is 8. So I'm going to sketch the rest of my cardioid. This is a quadrant 4. And ladies and gentlemen, as you can see, now, you know, my art skills are not that great. This is why I like Desmo so much. but Desmos has a nicer and more beautiful version of what I'm trying to express, and that's another cardioid. So, ladies and gentlemen, so this is the process, and over a few days, we've seen a few graphs of cardioids. So, what I'm going to suggest to you guys too now, if you said, okay, is that why you drew the answer here as well, so you can compare in your worksheet? Yeah, I want you guys to compare. I took it from Desmos, but it's a blue heart, not a red heart. It's on its side. But the process is reading off your points here. So this is the graphing technique that exists. There is no graphing technique in rectangular coordinates. You got to go to polar to do it. What do you guys think? Is that beautiful? Well, and then, I'm going to have you guys look at number 3. You can do that on your own. Of course, on your test and final, I give you this nice graph so that you guys you don't have to bring a special graph paper at all. I provide it for you guys, okay? So I just want to let you guys know that. The question was asked earlier. And then I'm going to go to the next situation called the what? Roses. And you go, Mr. Judge, there's roses? I told you math is pretty romantic. All right, hearts and roses. My God. It's mathematicians. Maybe that's what's wrong with them. They're always thinking of romance. Anyway, you say, what does it look like? Well, it's all based on these equations here. Now, notice what is new here for you. You might say, do you still have that A value? Yeah, we have a constant. A can be 1, by the way. A could be, And N is an even, so then you say, what's the main difference between what you had before, what you have now? See that N? There's an N there now. And now you say, okay, N is an even integer. So if N is even, do you guys know what even numbers are? Like if you see like 2 theta, 4 theta, and you can't even see my theta. Okay? So if you had like 2 theta, 4 theta, right, maybe 6 theta, and so on. How many leaves do you have? You have what's called 2n leaves. So you simply double. This will be 4 leaves, 8 leaves, 12 leaves. And then you say, what if n is an odd number? Like, 3 theta, 5 theta, 7 theta. Those are all nice odd numbers. Well, you have simply, again, what? 3 leaves, 5 leaves, 7 leaves. And is odd in leaves. So I drew a picture here for you guys of what you can see. Here's some roses. That's what we call roses. Over here you have a 3-leaf rose. Okay. So these are 4 leaves, just so you said, is that a picture of a 4-leaf rose? Yeah. Is that a picture of a 3-leaf rose? Yes. You got leaves. And I'm going to remark about this. This is something that you guys want to even consider sometimes in graphing, especially when it comes to roses. If the polar equation is unchanged, meaning it's the same, when you replace theta with minus theta, what does that mean? Do you guys know what that is if it's unchanged? When you replace theta with minus theta? Yeah, like cosine. right? This is what they mean. Cosine, that happens. I guess that's when it's an even. What they really mean is when it's even. Well, what happens when you have an even situation? It's symmetric about the what? The polar axis. Something's off here for me a little bit. I got to double check. If the polar equation is unchanged when you place r and minus r, then the graph is symmetric about the pole. Okay. If the polar equation is unchanged when I replace theta with pi minus theta, this is the cofunction identities. Anybody remember if you have any cofunction identities? You might say, well, you're going to give me this identity sheet. That reminds me, I got to make sure what? Let's go back. Let's scroll out. I don't think I could scroll out. Oh, yeah, I can. Can I? Yeah, here's this. Scrolling. We got our identity sheet. Remember this? The cheat sheet. I got to give you guys the cheat sheet. I think somewhere, we did some cofunction identities. Is that right? Oh, I don't know. That's pi minus 2. I guess it's not cofunction. It's not. I'm not awake yet. I apologize. Anyway, just looking at some of these here. Oh. Okay. Let's take a look at this first situation here. Let's see if we can figure something out. Now, I did these a little bit differently. Okay? I did this a bit differently in the sense that, oh, what did I do here? I gave you guys the graph first. Notice n is 2. Okay? So when n is 2, it's an even number. You got 4 leaves. So this is what you're seeing here. And again, this is the a value over here. Okay, you guys okay with that? Just looking for something here. All right. Easy breezy lemon squeezy. Okay, now you might say, well, how do we start to graph these here? Same way. You think of that, first of all, you graph r equals 2 cosine 2 theta. Remember about the period, though. What's the period? 2 pi over 2. So my period here is pi, okay? Now, you want to graph this to include all 4 quadrants. So go back and remember your graphing information. You might say, hey, Mr. Judge, is this why they did 2 cycles here? Okay? You graph 2 cycles here, not 1. Let's see if we can make sure we can write that. This is 2 cycles for your roses. Okay, and then this over here will be 2 pi. Now, you say, why do I need to do that? Even though this period here is pi, you got to do 2 cycles because you need all the quadrants. We need to graph what's going on in quadrant 1, quadrant 2, quadrant 3, quadrant 4. So this is why you have 2 cycles here. And that's going to be, again, r theta here. So just like before, r theta. But let's identify what everything is now. Okay? Because yes, I'll change my color. That's pi. This will be what? Pi over 2. Is that right? Halfway? And then the maximum value over here, this is going to be important for us. This is pi over 4. So the multiples are 1 pi over 4, 2 pi over 4. The minimum value would be what? 3 pi over 4. This is the one cycle information. But you're now going to say, oh, you have this first portion. It's not even quadrant 1 anymore. Second portion, this together is quadrant 1, by the way. Because that goes from 0 to pi over 2. Isn't that quadrant 1? Okay, you guys see what I'm saying? You see my point here for you guys? So that portion's quadrant 1. Yeah. Oh, let's see. What did I screw that up? Maybe I did. Uh-oh. Typo. Let's go to Desmos. 2 cosine 2 theta. I apologize. Let's turn you off. Y equals 2 cosine 2 theta. I hope I did not screw this up. And you're right. I think that looks like... Okay. Now, here's how we restrict our domain. Remember, we're going to restrict this domain. Where is this? 0. Well, I guess you could use this. 0 less than or equal to. You could spell out just theta here. And less than or equal to 2 pi. Okay, let's make this bigger now. And ladies and gentlemen, I can share with you all the gory details here. And in fact, well, here's one thing I can do. But the problem is, I think I really made this messed up. R equals 2 cosine 2 theta. Yeah, I really screwed it up. I believe this is not the right curve. It might be R equals 2 sine theta. Sine 2 theta. And let's do this. And yep, so I'm going to do this fix. Thank you for catching the screw up. This is R is 2 sine theta, 2 theta. Okay? So here's what I'm going to do. We're going to fix it easy. This is now what? Sine. You see what I'm saying? So we're back in business. Thank you. And now everything should be fine. Okay, so here's the polar curve. It's R is 2 sine theta. Let me write it here. Not theta, 2 theta. Can't see. So I can fix this when I get home. So I'm always fixing everything. There we go. Thank you for catching that. So now we're in business, okay? You guys okay with that? That's quadrant 1, by the way. So notice what's going on in quadrant 1, just to kind of compare these. Remember, we still need this point, which is 0, 0. We're still plotting r theta, okay? And we need this point over here, which will be what? R is 2. The angle's pi over 4. And then down here, the radius is 0, and the angle is pi over 2. So this is what you're looking for here. this, 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 here, here, here. Okay, now that's just that first rows. So you say, how do we start? You start at 0, 0. And I guess I didn't do it the same way, but here's my point. You start at 0, 0 here, okay? And then you rotate from 0 to pi over 4. And then the radius will be 2 at pi over 4. So this is where pi over 4 would be. It's 45 degrees. So that color here in orange, I know what I wanted to share with people. That's this portion right here. You go from 0 to what? 45 degrees. And that is radius of 2, angle pi over 4 here. Okay, I'm going to get rid of this. So I just want to share with you guys how that looks. Okay, that's the orange portion here, going from 0, 0 to 2 pi over 4 in orange. And then you go to 90 degrees, which is pi over 2, and you're back at 0. Is that right? So that's in green. Here's what I'm saying here. You go back to the pole. And that's what happens in quadrant what? 1 here, ladies and gentlemen. Now, similarly, you say, well, what's going on here now? Well, read these locations here. This is the next point, and the radius is -2 here. So we have to know how negative radiuses work. And the angle now is 3 pi over 4 here. Okay, that's this particular location here. Where are you? Here you are. And we're going to color this what? Maybe brown. So you're going to go to 3 pi over 4. Radius is -2. What's the angle of 3 pi over 4? You guys know? 135 degrees. So this is going to be going this way. So this is how that looks. You go from 90 degrees, pi over 2 now, to 3 pi over 4. And your radius is negative. So you start at 0. So you say, well, how does that look? Well, where are you at that angle? So this is the angle 3 pi over 4 here. My radius is on the opposite side. My radius is over here. Okay? So this is the point, -2, 3 pi over 4. It's on the opposite side. So how this is feeling is that you're going now this way. Okay? Remember, negative radius is on the opposite side of the pole. Now, the last portion here is 3 pi over 4 to 2 pi. And you say, where's this location? Here. Well, that location is radius 0, angle pi here. Right there. And that's in pink. So you're going to go from that 3 pi over 4 and a negative radius to the angle pi, which is 180, and you're back at the pole now. So you say, how does that look? You're going back to 0 there. And as you guys can see, just doing 0 to pi, we might have some symmetry here. Let's see what this means here, right? You see this? This is our curve. R equals what? 2 sine 2 theta. And it doesn't want to write. So what happens if I replace my theta? Should I replace theta with pi minus theta? What does R give you? 2 sine 2 pi minus what? 2 theta? Huh. There we go. Do we have a difference formula? What's the difference formula? Sine A minus B? Oh. So I'm going to use the difference formula here. What is sine A minus B? Isn't that what? And it would be helpful to get a pen that writes. Isn't that sine 2 pi using the difference formula? Sine 2 pi cosine what? 2 theta minus, so it's sine cosine minus cosine 2 pi sine what? 2 theta. By the difference formula. So double check. Well, this is 0. Isn't that negative 1, I think? What's cosine 2 pi? It's positive 1. This doesn't write. So this would be 2, ladies and gentlemen. What's that? That minus sine 2 theta? Something's bothering me here. That sine minus is sine cosine minus cosine sine. So it looks like we're okay. Yeah, anyway, isn't that minus what? 2 sine 2 theta? So something's not quite right. The polar equation is unchanged, replacing theta with pi minus theta. The graph is symmetric about the y-axis. Okay, so let's take a look. Let me do something here. Something's bothering me. I go back way up here. Let's find this out. Okay, this is in chapter 8. 2. Let's look at our symmetry properties. Yeah. Sine 2 pi cosine 2 theta minus cosine 2 pi sine 2 theta. Yeah, something's a bit odd. I'm not quite sure. It's supposed to be symmetric. Anyway, we're going to continue with this, okay? So the rest of it, you might say, what do I do here? Just so you guys can see. This location is going to be, we're now going to repeat the process. So you say, well, how do you repeat this process here? Let me erase this here. We're going to need this location here, this location, this goes to 2 pi. So if you find this, remember, these are all multiples of what? Pi over 4. So we go from 4 pi over 4 to pi over 4 to this next point, pi. So this is going to be what? 5 pi over 4. And then this is another pi over 4. 6 pi over 4. What does that give you? And this is another pi over 4. 7 pi over 4 over here. And then this, you're going to end up with a 2 pi. So these locations, looking at 2 cycles, you can continue. This is going to be radius again now is 2. Angle is 5 pi over 4. Radius is 0. Angle is 3 pi over 2. And down here, radius is negative 2. Angle is 7 pi over 4. And here, radius is 0. Angle is 2 pi. So you have here all these locations in terms of our theta. And I'm going to use the same exact colors. So this is the orange. We're going to go from pi to 5 pi over 4. Radius goes from 0 to 2. So you say, what does that look like? Pi to 5 pi over 4. Well, 5 pi over 4 is this angle down here, right? So that color again is orange. So you're going to go from here, radius is 0 to radius is 2. And that's this portion here. Radius went from 0 to 2. And then in green, you're coming back from radius is 2 to 0. And that angle is 5 pi over 4. So if you can see it here, to 3 pi over 2. 3 pi over 2 is 270. So you're going back to a radius of 0 here. So, and I think we used green. Now the next color was brown, right? So you're going from 0, 3 pi over 2 to a radius of negative 2, angle 7 pi over 4. So 7 pi over 4 again is this way. And it's a negative radius. So it's opposite the pole. So you're going back around this way. And then finally you say, oh, the negative radius going from that 7 pi over 4 to 2 pi in pink. You're coming back to 2 pi. Radius is negative 2 to 0. So this is coming back that way. So, ladies and gentlemen, a rose is done like you see here. And this is R is 2 sine 2 theta now, sine double theta here, okay? All right, now, there's something I do want to say about this. I need some scratch paper, though. Okay, R is 2 sine 2 theta. Let's go back. Let's get some scratch. What about the Cartesian coordinate? Rectangular coordinate version. equation. So the rectangular coordinate equation, right? You guys remember that? We can do that here. Now, here's what I'm going to say to you guys. How did we do it before? Because we didn't do it here. Well, you multiply both sides by what? R. Is that right? And so you got R squared going to be now 2R sine 2 theta. Now be careful here with this. Because yes, you can say R squared is what? X squared plus Y squared. You can replace it. But then that now leaves you with what? 2R sine 2 theta. Now be careful. You cannot say, I forget what color we use. I think it was green. This is not R sine theta. This is R sine 2 theta. So what do you do there then? You guys appreciate the issue? That's not R sine theta, so it's not green. You ever seen sine 2 theta before? Say yes. 2. Boy, my pen just doesn't want to work today. 2 sine theta cosine theta. What is that? I guess I need a... got to say note to self. Change your iPad tip. 2 sine theta cosine theta. Okay? You guys okay with that? Yeah. R, this will be now 2 times 2, which is what? 4R sine theta. Cosine theta. And that was no longer R, that was what? X squared plus Y squared here. Okay, you guys okay with that? Easy breezy lemon squeezy? Just kind of remark now, you say, well, what do I do this? What do I do with this now? Well, you have kind of a dilemma. Here's what I'm going to say. Now I'm going to say this. Multiply both sides by R squared. Okay? I'm going to try this out. What that means is on the left, you really get X squared plus Y squared, I think squared here, right? Will be the R squared 4R sine theta cosine theta. Okay? Because again, you got R squared being X squared plus what? Y squared. Okay, so you have another factor of X squared plus Y squared on the left. That's why you have squared. Now, I'm going to say use only one of the R's here. This is R now. Distribute one of the R's. Maybe you want to see that detail. So if I distribute only one, I'll get R now. 4R sine theta R cosine theta here. Okay? So now you have a factor R sine theta, and over here you have a factor R cosine theta. You say, why is that important? Because this is now Y, and this is X. Is that right? So on the right side, you have R now, and that's now 4 really XY, okay, on the right. And on the left, you got X squared plus Y squared squared. Yeah. Oh, no. You know why? This is the question. See this R? It's over here. This is times here. Yeah, I do. You're right. Well, you have a very good point. Here's what I'm saying. When you distribute, what do you guys see here? That's not addition. That's not addition or subtraction. If it were addition and subtraction, you're right. You got to multiply r to both. But if it's just a strict what? Multiplication, the order in which you multiply doesn't matter. So that r is multiplied here. And then finally, what do you think you can do here with this? Divide both sides by what? 4xy. Okay? So here's what I'm saying. You're going to get what? X squared plus y squared squared over, well, there's two things I can do. Let's do it this way. I can divide, I can do it this way. You know what we can do at this point? Yes, I could do it that way, but I think I'm going to be a little bit more elegant. You know what I'm going to do? I'm going to square both sides. Okay, when you square both sides, what do you think you get? You get x squared plus y squared to the what? Fourth power is r squared. I would say now square the 4xy. You're now going to get what? 16x squared y squared. You can now replace this with what? X squared plus what? Y squared. Okay, so now you have x squared plus y squared to the fourth power becomes 16x squared y squared times that x squared plus y squared. And then finally, ladies and gentlemen, can't you cancel a term? And you should get now x squared y squared to the third power becomes what? 16x squared y squared. Okay. Now double check. Whatever. Doesn't want to straighten out. This is the Cartesian coordinate version. Now, if I go over to Desmos, you say, can you check that out for me, please? Let's try this out. Hopefully this is not a problem. X squared plus what? Y squared, okay? And then that's raised to the what? Third power? Okay. 16 x squared. Uh-oh, we're coming on strong. Y squared, ladies and gentlemen. Sure enough, what's the deal? It looks like we're what? Oh, it's just so... It looks like we're good to go on that one, okay? See that? It is the same. Yay. Yeah, that symmetry thing is a little odd to me. I got to figure it out. Maybe it isn't symmetric about that. It looks like it is, but maybe it's not. I got to double check that. Now it's kind of a weird one. Using that famous identity here, ladies and gentlemen. So this is a rose to get back to you guys. And then I want to at least get this in for you guys. The very famous lemniscates. See if you guys can see. Now, I have two lemniscates here. What do they look like to you guys? Infinity sign, outstanding. That's what I want you guys to see. Now, this one's a lot easier. Lemniscates are easier, but be careful. They have what here? R squared on the lemniscates. So you might say, how do lemniscates use? Well, our symmetry properties. Let's look at this first one. This is r squared. It's not r. It's 4 cosine 2 theta. Hopefully that one's correct. I'm going to have to change my worksheet. Infinity. You say, Mr. Judge, how do you actually handle this one here? Well, you look at this as y is 4 what? Cosine 2 theta. Yes, again, your period is what? 2 pi over 2, and it equals pi. We're going to have to draw 2 cycles here so that our angle is between 0 and 2 pi, okay? And sure enough, it looks like we're right on this one here, okay? They say, oh, great. This is pi. Okay, so we need this location. This location, this location. This is pi over 2. Pi over 4, again, this is by pi over 4s again. So we need all those locations. This is radius is 4. Angle 0. This is radius is 0, angle pi over 4. Okay, now, this is r squared. This is theta. I just want to remark here about something. Okay, because remember, you say, is this my y? Y is r squared? Yes. Y-axis. But this is r squared now. We want to plot 4, or r theta. And here, you got to be careful here. Okay? You're really looking at the r. These are all r squared values. Okay? So this number, God, I can't get the highlighter. That's r squared. That's r squared. So for that first interval, here's our first interval. 0 to pi over 4. So I want you guys to notice this. When theta equals 0, what is r squared? R squared is 4. You with me on that? That's this first location here is what we're talking about. That point. That's an r squared value because they give us this. R squared is 4. So when the square is happening, there's just a little bit more work. What does that mean if r squared is 4? That means r is plus or minus square root of 4. So ladies and gentlemen, that means r is plus or minus 2. So what I'm getting at is you now have 2 radius values at 0. When the angle is 0, you got 2 radius values. You got 0, 2, and you got 0, minus 2. Okay? Because r squared is 4. So you say, well, what does that look like? Well, here's your angle, again, being what? 0. Okay? Radius is 2, and radius is negative 2. You got 2 points, because r squared can be negative, right? So remember, this is the location. 0, 2, and this is the location what? 0, negative 2. It is always opposite the what? The pole. So this one is extremely interesting here. There's your pole. And you say, well, how do I then go from a 0 degrees to 45 and my radius is 0? Well, if r squared is 0, you guys know, what does it mean if r squared is 0? That just means r is 0. So you're talking about the radius 0, angle pi over 4 here. So 45 degrees. Somehow you go back to a radius being what? And I apologize, ladies and gentlemen, this is really not to scale, because I can see that here. It's a funny thing. But that orange looks like this. It's not really to scale. So this goes from a radius of 2 to 0, and this goes from a negative 2 to 0. So you get both of those going on. And in theory, This is supposed to be, so you guys know, you're not supposed to cross that line. This is why I know it's not to scale. In theory, that's 45 degrees. Just so you guys know. It's not a 45-degree angle, but that's what's supposed to be happening. It's just when they, in Desmos, which you guys don't know, in graphing programs, it's not a true square, 1 to 1 sometimes. They have to have different dimensions for that rectangle. That's like how they call it rectangular coordinates, so that the curve looks kind of interesting. Just to let you guys know, that's supposed to be a 45-degree line, but it's not. It looks more closer to 60 degrees. But that's because this is not a true, you guys see how this is not a true square? You guys see my point? It's not a true, it's a rectangle. So the dimensions are off just to kind of get it to look okay. It's a graphing issue. But this is the most important thing. The next most important thing is that you do not care about these values here or these values over here. Does anybody know why you don't care? Because what's the radius over here? This means r squared is -4 down here, right? Isn't this where -4 is? And that means r is plus or minus square root of -4, which means your radius is really plus or minus 2i. Now, this is an imaginary number, ladies and gentlemen, complex numbers. So when the curve is below the theta axis or the x-axis, what do? You throw this out. It's gone. So we only care about what's going on here and here, above the theta or the x-axis, because now you went from the angle 3 pi over 4. You say, where is that angle 3 pi over 4? Same thing. It's not to scale. Right? You're going from 3 pi over 4 now to this angle here, which is pi. So again, you have r squared being +4, and you guys know that means two things. So when the angle is pi, your radius is +2, and the radius is -2. Because again, this is r squared equals 4 at that angle. We're looking at r squared now. So from 3 pi over 4 to pi, you got two radius values. You go from 0, right? You say, okay, what's going on? 3 pi over 4. That's in green. Well, 3 pi over 4 to pi, radius is 0 to -2 and 0 to +2. So you're back here and here. Okay, all because of this concept there. That's what I'm referring to. So you only care about what's above the what? Theta axis or x-axis, but don't forget r squared is what you're looking at. You're not looking at r. You have two values, and your radius for r can be negative. So this is how you graph the very famous lemniscate that you guys see here. There's two things going on there. And r squared is 4 cosine 2 theta. So if you said, wow, what's the Cartesian coordinate? You know, you got what? R squared is what? 4 cosine 2 theta? Well, you guys already know this is going to be what? This is x squared plus y squared equals 4 cosine 2 theta. Now, you're going to have to go back up here and maybe use an identity. Is there a cosine double angle that gives me anything I can use? But you got to be careful. Which one do we use? Right? Do I use maybe? Let's try this out. I'm going to have you guys. Isn't that cosine squared theta minus what? Should I use that one? In theory, I can. In theory, I can use that, right? Okay, you guys okay with that? So on the right side, it looks like I got 4 cosine squared theta minus 4 what? Sine squared theta. On the left side, I got x squared plus y squared. You know what I think I want to do? I'm going to multiply both sides again by what? R squared. Okay? Now, I know on the left, it gives me x squared plus y squared squared. But on the right, you know what it gives me? 4r squared cosine squared theta. Now, this is different from the last one. You say, how is that different? You know what you can do? You know what you have to do? You got to distribute. This is because you have what here? You got the minus sign, so you have to distribute that r squared. That's not what you had before. So I just want you to clarify that if you guys know what I'm saying? And then now I'll say this is going to be 4 what? X squared for y squared. Does anybody know why? Right? Isn't that x squared? Isn't this y squared? So at the end of the day, x squared plus y squared squared is, I'm going to factor out that 4. I'm going to keep it out. Okay? And I know I've been putting my final answers in black. Highlighting in blue just to be consistent here. So to remind you guys, let's see in Desmos if this is what it should be. Right? Come on, Desmos. Let's go back here. We're getting rid of this. Getting rid of this. Let's see. X squared plus y squared. Come out of there and say that is what? Squared. And that's supposed to equal 4 parentheses x squared minus y what? Squared. Okay. There's a nice infinity sign. But what was the curve again? R squared is 4. R squared equals 4 cosine 2 theta. Oh, and I know what happens with Desmos. It doesn't like that. Desmos wants you to use the square root. Sorry about that. R equals square root 4 cosine. You can't use r squared there. Cosine 2 theta. There you go. In blue. So let's toggle. In red, Cartesian. In blue, polar. Cartesian, polar. Ladies and gentlemen, Mr. Judge only made one typo on his worksheet that kind of messed us up. I'll accept that. I'll have to change that. I don't know what's going on. I'll have to change that. But ladies and gentlemen, so on test 4, you're going to expect only up to the lemniscates. Okay, you guys okay with that? So when you guys go home and you go, I'm doing this study guide. Oh no, my test 4 study guide, where is it? Go, that Mr. Judge, what did he do? Did he give me anything different? Let's see. Did he go up to a lemniscate? Just think cardioids, roses, and lemniscates. I'll have to go back. I can see a couple of these. This is like a circle. The last 3 curves are circles. You guys see that? They're circles. And yeah, so you're not going to do 4 minus 2 cosine theta. You don't have that. So you're not going to do 34, 35, and 36. You can do the others though. So when I go home, I have to say, don't do 34, 35, or 36 unless you want to. Do it on the worksheet. Look at my worksheets I gave you guys there, or the worksheets that are where. Because that last one, 34, 35, and 36, we didn't go over. 34, 35, and 36 is, it's a limicon. We didn't do the limicons. Okay, see this here? These are limicons. They look like a dimpled, well, there's a dimple there. We didn't do limicons. This is it's a convex limicon. We didn't do the limicons. You guys can look it over if you like. It's probably easier than all the others. But we didn't cover limicons, so that won't be on test 4. Okay? So, okay, you guys, I'll see you guys on Monday early if you like. Take care and stay safe, and have a wonderful day.